Hello friends, in this session we are going to discuss a question that came in GATE 2014 and it comes from the topic of set associative mapping. So this time I'm going to solve it on live with you. So let's see where the question is. So the question is a set associative mapping, a four-way set associative cache memory unit with a capacity of 16 kilobytes is built using a block size of 8 words. So I'm going to underline a little bit of things which I feel are important. This, and then with a block size of 8 words. The word length is 32 bits. Word length is 32 bits. And the size of the physical address space is 4 gigabytes. Right. So 4 GBs. And the number of bits for the tag field have been asked. So they've asked the number of bits for the tag field. So what is the first rule? The first rule says, first of all, jot down the things that you have been given in the question. So we are going to write the given things first of all. Right. So what do we have? First of all, we have four-way set associative. They've written. So four-way set associative. What can we infer from this? We can infer that there are 4 blocks per set. 4 blocks per set. Right. So next thing they say that there is a capacity of the cache memory block is of capacity of 16 kilobytes. So cache size, we can say cache size is 16 kilobytes. Next thing they say that the block size is 8 words. So block size is 8 words. Next they say the word length is how much? It is 32 bits. So that means we are basically going to use it over here. And the size of physical address space. The size of physical address space is how much? It is 4 gigabytes. So I'm slightly moving it up. So it is physical address space is 4 gigabits. Right. Yes. And finally, what do they require? They require us to find the tag bits. Yes. Now let's simplify the things. First of all, we have cache size is 16 kilobytes and the block size is this, word length is this, so on. So one thing I should be very clear of, I am solving the question of set associative mapping technique. So what should be the next thing? The next step should be to draw the diagram first of the set associative mapping addressing scheme, right? So I should draw the diagram first. So what is the diagram? How does it look like? We have 3 things over here. We have the tag bits, right? Then we have the set bits and finally the word bits. Right, we have the 3 things. Now I'm very clear of what I need to find and how I'm going to get, right? So 4 blocks per set I am here. Then first of all I should know the total number of bits I'm going to put over here, right? So that is going to come from here. Physical address space is 4 gigabytes. Let's just convert it into the respective thing. It is 2 to power 2 into gigabytes. Now you know that 2 to power 10 bytes is your kilobytes, right? Then 2 to power 20 becomes mega, 2 to power 30 becomes giga. So I'm going to directly write 2 to power 30 over here bytes. So that means this entire thing is equals to 2 to power 32 bytes. This entire thing can be represented with the help of 32 bits. So I'm going to label it as 32. So we are done with this part now. Next I'm going to look for this word. So word size, the word length has been given as 32 bits. This is going to give me the number of combinations I require to represent the word length, right? So this is nothing but 2 to power 5. That means the number of bits that are going to come over here are 5. Done with this as well. Then we are going to find the set bits. Now this is what is very important. So first of all, what do we require for this? We require the number of blocks present in cache and then the number of sets present in cache, right? So first of all, let's find the number of blocks in cache. How do we find the number of blocks in cache? Number of blocks in cache. Now this is equals to size of cache upon size of one block. This is equals to what? Now we know size of cache is 16 kilobytes. So I'm just going to write 16 into 2 to power 10 bytes for kilobytes. Then size of one block is given as 8 words and one word is 32 bits. That means I need to convert the entire thing into bits, right? Or I can convert it into bytes as well. So let's simplify it. Let's convert the entire thing into bytes. So 8 into 32 would be the thing to be written over here. 8 words and one word is of 32 bits. So 8 into 32. Now if I convert the entire thing into 2 powers, what will I get? I'll be writing down 2 to power 4 into 2 to power 10 into 2 to power 3 for converting these bytes into bits. And we know that 1 byte is equals to 8 bits. So 2 to power 3 over here. Then 2 to power 3 for this, 2 to power 5 for this. And when you simplify the things, you get to know that this is 2 to power 7, including this and this. This is 2 to power 8 combinedly. So you can write that this is 2 to power 10 upon 2, which is nothing but 2 to power 9, which is 512. Right. So this is 512. So these are the number of blocks in cache. But what do we require? We require the number of sets. Right. So number of sets. Number of sets is what I'm going to find the next. Number of sets is what? We have written that there are 4 blocks per set. So in one set there are 4 blocks. If I have total these many of blocks, how many sets would be there? 512 divided by 4. Right. So this is what? This is 128. Right. Now if I want to put something over here, what are these? These are the number of bits I would require to represent these many combinations. So this is nothing but the set bits is equals to log 2 of number of sets in cache, and this is going to be log 2 of 128, which is 2 to power 7. So log 2 of 2 to power 7, which is 7. Sorry, it just became a bit untidy. So it is 7. So we have 7 over here, 5 over here. So how many tag bits do you get? 7 plus 5, 12. If you just subtract it, it from 32, you get it as 20. So there are 20 tag bits for this. Fine. So 5 word bits, set bits are 7, tag bits are 20. So that's all for this session, for this question of GATE 2014. I'm sure you would have got a greater clarity of the concept of set associative mapping. Stay tuned for more upcoming videos, for more good work coming up. Thank you. Thank you, friends.